Universal Serial Bus, USB, is an industry standard, developed by USB Implementers Forum, USBF, for digital data transmission and power delivery between many types of electronics. It specifies the architecture, in particular the physical interfaces, and communication protocols to and from hosts, such as personal computers, to and from peripheral devices, e.g. displays, keyboards, and mass storage devices, and to and from intermediate hubs, which multiply the number of a host's ports. Introduced in 1996, USB was originally designed to standardize the connection of peripherals to computers, replacing various interfaces such as serial ports, parallel ports, game ports, and Apple Desktop Bus, ADB, ports. Early versions of USB became commonplace on a wide range of devices, such as keyboards, mice, cameras, printers, scanners, flash drives, smartphones, game consoles, and power banks. USB has since evolved into a standard to replace virtually all common ports on computers, mobile devices, peripherals, power supplies, and manifold other small electronics. In the latest standard, the USB-C connector replaces many types of connectors for power, up to 240 W, displays, e.g. DisplayPort, HDMI, and many other uses, as well as all previous USB connectors. As of 2024, USB consists of 4 generations of specifications: USB 1.x, USB 2.0, USB 3.x, and USB 4. The USB 4 specification enhances the data transfer and power delivery functionality with a connection-oriented tunneling architecture designed to combine multiple protocols onto a single physical interface so that the total speed and performance of the USB 4 fabric can be dynamically shared. In particular, USB 4 supports the tunneling of the Thunderbolt 3 protocols, namely PCI Express, PCIe, Load/Store Interface, and DisplayPort, Display Interface. USB 4 also adds host-to-host interfaces. Each specification subversion supports different signaling rates from 1.5 and 12-bit/S half duplex in USB 1.0/1.1 to 80-bit/S full duplex in USB 4 2.0. USB also provides power to peripheral devices. The latest versions of the standard extend the power delivery limits for battery charging and devices requiring up to 240 watts as defined in USB Power Delivery, USB PD, Rev. v3.1. Over the years, USB PD has been adopted as the standard power supply and charging format for many mobile devices, such as mobile phones, reducing the need for proprietary chargers. USB was designed to standardize the connection of peripherals to personal computers, both to exchange data and to supply electric power. It has largely replaced interfaces such as serial ports and parallel ports and has become commonplace on various devices. Peripherals connected via USB include computer keyboards and mice, video cameras, printers, portable media players, mobile, portable, digital telephones, disk drives, and network adapters. USB connectors have been increasingly replacing other types of charging cables for portable devices. USB connector interfaces are classified into 3 types: the many various legacy Type A, upstream, and Type B, downstream, connectors found on hosts, hubs, and peripheral devices, and the modern Type C, USB-C, connector, which replaces the many legacy connectors as the only applicable connector for USB 4. The Type A and Type B connectors came in standard, mini, and micro sizes. The standard format was the largest and was mainly used for desktop and larger peripheral equipment. The mini USB connectors, Mini A, Mini B, Mini AB, were introduced for mobile devices. Still, they were quickly replaced by the thinner micro USB connectors, Micro A, Micro B, Micro AB. The Type C connector, also known as USB-C, is not exclusive to USB, is the only current standard for USB, is required for USB 4, and is required by other standards, including modern DisplayPort and Thunderbolt. It is reversible and can support various functionalities and protocols, including USB, some are mandatory, and many are optional, depending on the type of hardware, host, peripheral device, or hub. USB specifications provide backward compatibility, usually resulting in decreased signaling rates, maximal power offered, and other capabilities. The USB 1.1 specification replaces USB 1.0. The USB 2.0 specification is backward compatible with USB 1.0/1.1. The USB 3.2 specification replaces USB 3.1 and USB 3.0, while including the USB 2.0 specification. USB 4 functionally replaces USB 3.2 while retaining the USB 2.0 bus operating in parallel. The USB 3.0 specification defined a new architecture and protocol named SuperSpeed, aka SuperSpeed USB, marketed as SS, which included a new lane for a new signal coding scheme, 8B/10B symbols, 5Gbit/S, later also known as Gen 1, providing full duplex data transfers that physically required 5 additional wires and pins, while preserving the USB 2.0 architecture and protocols and therefore keeping the original 4-pin/wires for the USB 2.0 backward compatibility, resulting in 9 wires, with 9 or 10 pins at connector interfaces. ID pin is not wired, in total. The USB 3.1 specification introduced an enhanced SuperSpeed system, while preserving the SuperSpeed architecture and protocol, SuperSpeed USB, with an additional SuperSpeed Plus architecture and protocol, aka SuperSpeed Plus USB, adding a new coding schema, 128B/132B symbols, 10 Gbit/S, also known as Gen 2, for some time marketed as SuperSpeed Plus, SS Plus. The USB 3.2 specification added a second lane to the enhanced SuperSpeed system besides other enhancements so that the SuperSpeed Plus USB system part implements the Gen 1x2, Gen 2x1, and Gen 2x2 operation modes. However, the SuperSpeed USB part of the system still implements the 1-lane Gen 1x1 operation mode. Therefore, 2-lane operations, namely USB 3.2 Gen 1x2, 10 Gbit/S, and Gen 2x2, 20 Gbit/S, are only possible with full-featured USB-C. As of 2023, they are somewhat rarely implemented. Intel, however, started to include them in its 11th generation SoC processor models, but Apple never provided them. On the other hand, USB 3.2 Gen 1x1, 5 Gbit/S, and Gen 2x1, 10 Gbit/S, have been quite common for some years. The Universal Serial Bus was developed to simplify and improve the interface between personal computers and peripheral devices, such as cell phones, computer accessories, and monitors, when compared with previously existing standard or ad hoc proprietary interfaces. From the computer user's perspective, the USB interface improves ease of use in several ways. The USB interface is self-configuring, eliminating the need for the user to adjust the device's settings for speed or data format, or configure interrupts, input/output addresses, or direct memory access channels. USB connectors are standardized at the host, so any peripheral can use most available receptacles. USB takes full advantage of the additional processing power that can be economically put into peripheral devices so that they can manage themselves. As such, USB devices often do not have user-adjustable interface settings. The USB interface is hot swappable, devices can be exchanged without shutting the host computer down. Small devices can be powered directly from the USB interface, eliminating the need for additional power supply cables. Because the use of the USB logo is only permitted after compliance testing, the user can have confidence that a USB device will work as expected without extensive interaction with settings and configuration. The USB interface defines protocols for recovery from common errors, improving reliability over previous interfaces. Installing a device that relies on the USB standard requires minimal operator action. When a user plugs a device into a port on a running computer, it either entirely automatically configures using existing device drivers, or the system prompts the user to locate a driver, which it then installs and configures automatically. The USB standard also provides multiple benefits for hardware manufacturers and software developers, specifically in the relative ease of implementation. The USB standard eliminates the requirement to develop proprietary interfaces to new peripherals. The wide range of transfer speeds available from a USB interface suits devices ranging from keyboards and mice up to streaming video interfaces. A USB interface can be designed to provide the best available latency for time-critical functions or can be set up to do background transfers of bulk data with little impact on system resources. The USB interface is generalized with no signal lines dedicated to only one function of one device. Limitations. As with all standards, USB possesses multiple limitations to its design. USB cables are limited in length, as the standard was intended for peripherals on the same tabletop, not between rooms or buildings. However, a USB port can be connected to a gateway that accesses distant devices. USB data transfer rates are slower than those of other interconnects such as 100 gigabit Ethernet. USB has a strict tree network topology and master/slave protocol for addressing peripheral devices. Slave devices cannot interact with one another except via the host, and two hosts cannot communicate over their USB ports directly. Some extension to this limitation is possible through USB on-the-go, dual-role devices, and protocol bridge. A host cannot broadcast signals to all peripherals at once, each must be addressed individually. While converters exist between certain legacy interfaces and USB, they might not provide a full implementation of the legacy hardware. For example, a USB to parallel port converter might work well with a printer, but not with a scanner that requires bidirectional use of the data pins. For a product developer, using USB requires the implementation of a complex protocol and implies an intelligent controller in the peripheral device. Developers of USB devices intended for public sale generally must obtain a USB ID, which requires that they pay a fee to the USB Implementers Forum, USBF. Developers of products that use the USB specification must sign an agreement with the USBF. Use of the USB logos on the product requires annual fees and membership in the organization. A group of 7 companies began the development of USB in 1995, Compaq, DEC, IBM, Intel, Microsoft, NEC, and Nortel. The goal was to make it fundamentally easier to connect external devices to PCs by replacing the multitude of connectors at the back of PCs, addressing the usability issues of existing interfaces, and simplifying software configuration of all devices connected to USB, as well as permitting greater data transfer rates for external devices and plug-and-play features. Concepts of the 1979 Atari SIO serial bus, of the 8-bit Atari computers, and the 1980 IEEE 488-derived Commodore bus, and Hewlett-Packard's HPIL bus pioneered this approach. A consortium led by Apple, and containing Sony, Panasonic, Matsushita, LG, Toshiba, Hitachi, Canon, Philips Electronics, Compaq, Thomson, and Texas Instruments, would develop the concept further, from 1986, as the IEEE 1394 Firewire standard and patent pool. Joseph C. DeCure, originally of Atari, then Commodore, and a designer of the Atari SIO Common Bus, would work on the USB project, for Microsoft, obtaining one of the related US patents. Ajay Bhatt and his team worked on the standard at Intel. The first integrated circuits supporting USB were produced by Intel in 1995. Released in January 1996, USB 1.0 specified signaling rates of 1.5 Mbit/s, low bandwidth or low speed, and 12 Mbit/s, full speed. It did not allow for extension cables, due to timing and power limitations. Few USB devices made it to the market until USB 1.1 was released in August 1998. USB 1.1 was the earliest revision that was widely adopted and led to what Microsoft designated the legacy-free PC. Neither USB 1.0 nor 1.1 specified a design for any connector smaller than the standard Type A or Type B. Though many designs for a miniaturized Type B connector appeared on many peripherals, conformity to the USB 1.x standard was hampered by treating peripherals that had miniature connectors as though they had a tethered connection, that is, no plug or receptacle at the peripheral end. There was no known miniature Type A connector until USB 2.0, revision 1.01, introduced one. USB 2.0 was released in April 2000, adding a higher maximum signaling rate of 480 mbit/s, maximum theoretical data throughput 53 MB/s, named high speed or high bandwidth, in addition to the USB 1.x full speed signaling rate of 12 mbit/s, maximum theoretical data throughput 1.2 MB/s. Modifications to the USB specification have been made via engineering change notices, ECNs. The most important of these ECNs are included into the USB 2.0 specification package available from usb.org. Mini-A and Mini-B connector. Micro USB cables and connectors specification 1.01. Interchip USB supplement. On-the-go supplement 1.3 USB on-the-go makes it possible for two USB devices to communicate with each other without requiring a separate USB host. Battery charging specification 1.1 added support for dedicated chargers, host chargers behavior for devices with dead batteries. Battery charging specification 1.2, with increased current of 1.5 A on charging ports for unconfigured devices, allowing high-speed communication while having a current up to 1.5 A. Link Power Management Addendum ECN, which adds a sleep power state. The USB 3.0 specification was released on November 12, 2008, with its management transferring from USB 3.0 Promoter Group to the USB Implementers Forum, USBF, and announced on November 17, 2008 at the Superspeed USB Developers Conference. USB 3.0 adds a new architecture and protocol named Superspeed, with associated backward-compatible plugs, receptacles, and cables. Superspeed plugs and receptacles are identified with a distinct logo and blue inserts in standard format receptacles. The Superspeed architecture provides for an operation mode at a rate of 5.0 bit/s, in addition to the three existing operation modes. Its efficiency is dependent on a number of factors including physical symbol encoding and link level overhead. At a 5 bit/s signaling rate with 8b/10b encoding, each byte needs 10 bits to transmit, so the raw throughput is 500 MB/s. When flow control, packet framing and protocol overhead are considered, it is realistic for about 2/3 of the raw throughput, or 330 MB/s to transmit to an application. Superspeed's architecture is full duplex. All earlier implementations, USB 1 to 2, are half duplex, arbitrated by the host. Low power and high power devices remain operational with this standard, but devices implementing Superspeed can provide an increased current of between 150 mA and 900 mA, by discrete steps of 150 mA. USB 3.0 also introduced the USB Attached SCSI Protocol, UASP, which provides generally faster transfer speeds than the bulk-only transfer, protocol. USB 3.1, released in July 2013, has two variants. The first one preserves USB 3.0 Superspeed architecture and protocol and its operation mode is newly named USB 3.1 Gen 1, and the second version introduces a distinctively new Superspeed Plus architecture and protocol with a second operation mode named as USB 3.1 Gen 2, sometimes marketed as Superspeed Plus USB, contrary to USBF recommendation. This doubles the maximum signaling rate to 10 bit/s, later marketed as Superspeed USB 10 Gbps, then simply USB 10 Gbps, while reducing line encoding overhead to just 3% by changing the encoding scheme to 128B/132B. USB 3.2, released in September 2017, preserves existing USB 3.1 SuperSpeed and SuperSpeed Plus architectures and protocols and their respective operation modes, but introduces two additional operation modes, USB 3.2 Gen 1x2 and USB 3.2 Gen 2x2, with combined signaling rates of 10 and 20 Gbps, raw data rates of 1212 and 2424 MB/s. The increase in bandwidth is a result of two-lane operation over the additional wires included in all full-featured USB-C cables. Naming scheme. Starting with the USB 3.2 specification, USB-if introduced a new naming scheme. To help companies with the branding of the different operation modes, USB-if recommended branding the 5, 10, and 20 Gbps capabilities as SuperSpeed USB 5 Gbps, SuperSpeed USB 10 Gbps, and SuperSpeed USB 20 Gbps, respectively. In 2023, they were replaced again, removing SuperSpeed, with USB 5 Gbps, USB 10 Gbps, and USB 20 Gbps. With new packaging and port logos. The USB 4 specification was released on August 29, 2019 by the USB Implementers Forum. The USB 4 2.0 specification was released on September 1, 2022 by the USB Implementers Forum. USB 4 is based on the Thunderbolt 3 protocol. It supports 40 Gbps throughput, is compatible with Thunderbolt 3, and backward compatible with USB 3.2 and USB 2.0. The architecture defines a method to share a single high-speed link with multiple end device types dynamically that best serves the transfer of data by type and application. During CES 2020, USB-if and Intel stated their intention to allow USB 4 products that support all the optional functionality as Thunderbolt 4 products. USB 4 2.0 with 80 Gbps speeds was to be revealed in November 2022. Further technical details were to be released at two USB Developer Days scheduled for November 2022. The USB Mass Storage Device Class, MSC or UMS, standardizes connections to storage devices. At first intended for magnetic and optical drives, it has been extended to support flash drives and SD card readers. The ability to boot a right-locked SD card with a USB adapter is particularly advantageous for maintaining the integrity and non-corruptible, pristine state of the booting medium. Though most personal computers since early 2005 can boot from USB mass storage devices, USB is not intended as a primary bus for a computer's internal storage. However, USB has the advantage of allowing hot swapping, making it useful for mobile peripherals, including drives of various kinds. Several manufacturers offer external portable USB hard disk drives, or empty enclosures for disk drives. These offer performances comparable to internal drives, limited by the number and types of attached USB devices, and by the upper limit of the USB interface. Other competing standards for external drive connectivity include eSATA, ExpressCard, FireWire, IEEE 1394, and most recently Thunderbolt. Another use for USB mass storage devices is the portable execution of software applications, such as web browsers and VoIP clients, with no need to install them on the host computer. Thank you for watching this video.